You know, one of the most incredible things happening in AI right now is that we're teaching machines how to read our most complex medical scans. It sounds like science fiction, but it's real. So let's break down how this actually works, and really what it means for the future of medicine.
The whole story here really kicks off with a massive and very human problem. Every single day, our hospitals produce this absolute tidal wave of medical images. And as this quote gets at, we just don't have enough human experts to look at them all, not with the speed and the accuracy that's needed. So the need for an automatic, tireless assistant, well, it's not just a nice to have anymore, it's fast becoming a necessity.
Really think about it for a second. Radiologists spend their entire careers hunting through these incredibly detailed scans. They're searching for the faintest, most subtle little clues of disease. It is an unbelievably high-stakes, high-volume job that is practically begging for a technological partner. So the big question is, how in the world do you get a machine to help with a task that complex?
Now, the solution isn't about, just programming the computer with a long list of medical rules. No, it's about something way more profound. We have to teach it how to see and how to learn from what it's seeing, almost like a human apprentice would.
The key that really unlocks all of this is a technology called deep learning. And as you can see in this diagram, it's a specialized field inside of machine learning, which itself is part of the bigger world of AI. It's this deep learning part that gives the AI the power to truly learn from images on its own, instead of just following our instructions. So what's the big deal here? What's the fundamental difference? Well, with the older kind of machine learning, on the left, an expert had to sit down and manually tell the machine, hey, look for this shape, look for this texture. But with deep learning, over on the right, the network figures out what's important all by itself, just by looking at thousands and thousands of examples. It's the difference between being told what to look for and actually learning how to look. That's a game changer.
Okay, so how does this automatic learning actually work? Let's pop the hood and take a look inside the brain of this medical AI so we can really understand how it goes from just seeing pixels to spotting anomalies in a scan.
The engine that's purpose-built for this job is called a convolutional neural network, or a CNN for short. Now, don't let the name intimidate you. The best way to think of it is as the AI's own visual cortex. It's the part of the system that's designed from the ground up to process and make sense of visual stuff. This is what powers the whole thing. The whole process inside that CNN is basically a repeating cycle of these three key steps. First, it convolves, which just means it scans the image with filters to find really basic patterns like edges and textures. Then, it activates, which is where it decides which of those patterns are actually meaningful. And finally, it pools, where it summarizes the important findings to start seeing the bigger picture. This cycle, find, decide, summarize, it just repeats over and over, building a smarter understanding with every single pass. So that first step, convolution, it's kind of like giving the AI a whole set of digital magnifying glasses. Each one is a filter that's designed to spot one very specific feature. One might be looking for just horizontal lines, another for a certain kind of texture, and another for a circular shape. And that pooling step, it's a lot like squinting. You know how when you squint at something, you kind of blur out all the tiny, irrelevant details? It helps you see the main objects and shapes much more clearly. The AI does the exact same thing, summarizing the important features it found to make the image simpler to understand. And what's wild is that this whole complex process, from finding edges to seeing the big picture, it's all built from one surprisingly simple component you see here, the artificial neuron. It's the basic, fundamental building block of the entire network. Its only job is to take in signals, process them, and then pass a new signal along. That's it.
But here's where the real magic happens. You take millions of these simple little neurons and you connect them together in layers, just like you see in this diagram. Information flows forward through this network, and each layer learns to recognize more and more complex patterns than the one before it. So, the first layer might just see lines and curves, but the next one might combine those to see shapes, and a layer way down the line might learn to recognize an entire organ.
And by stacking that simple process, convolve, activate, and pool across many, many layers, you get these legendary, incredibly powerful architectures like AlexNet and LeNet-5. It's this depth that allows them to look at a complicated medical scan and identify subtle, intricate patterns that might even be totally invisible to the human eye.
But there's a catch. And trust me, it's a big one. These deep learning models are incredibly data hungry. To become an expert, they need to see millions of examples. So what do you do when you don't have millions of labeled medical scans, which, let's be honest, are often rare, private, and really hard to get your hands on?
This is what's known as the medical data problem, and it's one of the biggest hurdles in bringing AI into healthcare. How can you possibly train an effective AI doctor if you can't give it enough textbooks to study from?
Well, the solution is this absolutely brilliant workaround called transfer learning. The idea is just genius in its simplicity. You don't start from scratch. You take an AI that has already become an expert at general vision by training it on millions of internet images. We're talking cats, dogs, cars, you name it. That AI has already learned the fundamentals of sight, what edges look like, what shapes are, what textures are.
Then, you transfer that pre-existing knowledge to your new medical task. And as this slide shows, you've got two main ways to go. On the left, feature extraction uses the pre-trained network as it is, which is super fast and simple. But on the right, you can fine-tune it. You take that powerful network and you just make some small adjustments using your limited medical data. The second method is often way more accurate. It's really a brilliant shortcut to creating a specialist.
So this technology is already moving out of the research lab and straight into hospitals. But what we've seen so far, it's just the very beginning. The next wave of research is pushing way beyond simple image recognition. It's starting to tackle even bigger, more fundamental questions about what the future role of AI in medicine is going to be. And these are some of the really profound questions researchers are asking right now. Can we teach an AI to truly reason about a patient's condition, not just spot a pattern? Can it learn new medical specialties without totally forgetting what it already knows? The ultimate goal here is to move beyond just recognizing patterns to something that's much, much closer to genuine medical intelligence.
And that, of course, leads us to the ultimate question. Is this technology on a path to one day replace human doctors, or will it evolve into their single most powerful diagnostic tool, an expert partner that helps them save more lives? The answer to that is going to shape the future of healthcare for every single one of us.
Like and subscribe for more content like this.